Hello everyone, my name is Denis Antipov, and in this talk I am presenting our joint work with Annette Neumann and Frank Neumann about the evolution diversity optimization on OneMinMax. In many usual optimization problems, our aim is to find the best solution according to some fitness function. However, in the real world, we often have situations when some of the solutions might be infeasible due to expert knowledge or just are not so much better than others. For example, when you ask your favorite Maps app about the optimal route to your workplace, the best route might be this one, but you know that this intersection is too stressful, so you would prefer to choose between these two. And usually when this is the case for an optimization problem, then the expert who makes the final decision wants to have a diverse set of solutions which are really different from each other, so that he could definitely choose at least one which is feasible in all the senses. However, problem of finding such diverse set of solutions is much harder than just finding one best solution, because the search is performed in the space of populations of sets of solutions, and it means that the dimensionality of this problem is much higher. However, evolutionary algorithms are designed to evolve the populations, so it is quite easy to just add some additional mechanisms so that they evolve those populations not only by the fitness of the individuals but also by improving the diversity of the set of the solutions of the population. In the multi-objective domain, usually we aim at finding a set of Pareto optimal solutions, but here we also can struggle from adding some additional constraints after we already found this Pareto front. And if this Pareto front is not diverse enough, then probably some additional constraints might just make all our solutions infeasible, and therefore when we want to don't want to rerun the algorithm, we just want to get a diverse set of Pareto optimal solutions. And so the aim of EDO in the multi-objective domain is usually to get a Pareto optimal set of solutions which are really different from each other according to some measure, and an additional goal is to also spread the set as wide along the Pareto front as possible. It is not a very well studied and well understood process of how evolutionary algorithms optimize diversity, especially in the multi-objective domain. So, however, Siri is very well known to bring some valuable insights about how EVs work and to help to improve their performance. So the existing results, theoretical results in the context of EDO are mostly about single objective problems like OneMinMax and leading ones and some submodular functions, and also there were some results about combinatorial functions like terminal salesperson problem or quadratic assignment, but both of them were without any restriction on the fitness which we want in our population. And there are only two works which considered a multi-objective setting. It is not so much compared to how many theoretical works appeared in other domains of evolutionary computation, and the reason we have so few results, is that it is really hard to analyze the population dynamics, and especially in multi-objective problems. So in this paper, in this work, we actually tackled the theoretical questions empirically, and we studied what is the minimum time of the simple evolutionary multi-objective optimizer, which also optimizes diversity D on OneMinMax, and we found out that its runtime grows approximately as fast as n square, where n is the problem size. And we also studied the Hamming distances between the neighboring individuals in the Pareto front, because it has previously been a big issue in the theoretical analysis. We also show an example of a suboptimal population, which is impossible to escape via only 1-bit flips, so that 2-bit flips are essential here. So we study in this work the GECCO D, which looks like the typical GECCO. It keeps a population of solutions which are not dominated, like at the moment they are Pareto optimal among the individuals which have been evaluated. and it generates new solutions, usually by the standard bit mutation, and if this new solution is not dominated by any solution, then population, it goes to the population, and we remove all the dominated solutions from the population, dominated by this new one. The only difference of this algorithm from the original vanilla GECCO is that when we get individual whose fitness is already in the population, then we decide which one to take according to the diversity measure, the diversity contribution to the population. So we only break ties and optimize diversity like that. So the OneMinMax problem, which we also study here, is a simple benchmark problem which has two objectives: the number of ones in the bit string and number of zeros in bit string. So the Pareto front of this problem consists of n+1 values of form I n minus I, for I from 0 to n, and all points in the search space are in the Pareto front. So we don't care about how we reach the Pareto front, we only care about how we spread over the Pareto front. And it was previously shown that the GECCO can spread over the Pareto front in n square log n iterations, and the previous estimates of the runtime of diversity optimization on this problem show that we need n cube log n iterations to find the optimal diverse population, but when we start from the second best diversity, then we only need n square iterations, and we will discuss this later in more details. So in these problems, as well as in the previous studies, we consider the optimization of the diversity measure, which is called the total Hamming distance. And this measure is defined as the pairwise sum of Hamming distance in the population, like over all the pairs of individuals. However, it is easier to use this alternative definition, which is let me explain it in more details. Like when we consider population, which is written like as bit strings, and consider the first position, then this 0 contributes to this sum of Hamming distances only when we consider a pair of this individual with any of these individuals with a 1 bit in the first position, this 0 bit as well, and this 0 bit as well. So the contribution of this position to this sum is the number of zeros in this position multiplied by the number of ones in this position, which can be written like that. We can just sum up this contribution over all positions. And it is easy to see that the contribution of each position is maximized when the number of ones is as close as possible to the number of zeros. And from here we also can build the perfect diversity, where we build the first half of the population, like for OneMinMax function. Like we can build the first part of the Pareto front in any way, and then we can just invert bit strings to get a perfectly balanced number of 0 and 1 bits in each position. And the worst diversity is when each position is as imbalanced as possible, and it can be reached when we first take 1 bits and then 0 bits. We will use this worst diversity in some of our experiments. So previously there was a discrepancy between theoretical results, which haven't been covered so far, and namely in 2016 it was shown that the total runtime of diversity optimization is n cube log n, and the main proof idea was that when we are in distance d from the optimal, when our diversity measure is by d less than optimal, then we have something like d 2-bit flips, which we can make to improve the diversity, and each bit flip is made with probability 1 over n cube, and the Kaplan collector effect yields this bound. Last year it was shown that actually we can optimize it from distance like 2 from the optimal in n square iterations, because the number of such good bit flips which help us to reach the optimal diversity changes a lot, and it's often linear, and from that state we can reach the optimally diverse population. However, because of this complication of dynamics, the Kaplan collector argument doesn't work anymore. So our question was, what is the actual runtime? So is it true that it is less than n cube? and for this reason we try to initialize the GCMD with different populations, and the initialization methods were single, when we just take a single point, so we allow it to first cover the Pareto front and then optimize. When we like all of those runs which start at the Pareto front, we call the natural initialization. So like we first take a point, we spread the Pareto front, and only then we start to current iterations. The worst initialization is the population with the worst diversity, which we discussed in the previously, and the random is when we generate each point in the Pareto front randomly with like the predefined number of 1 bits. And we see that for all initialization types, the runtime normalized by n square log n doesn't grow, which means that most probably this is the reason, this is the true asymptotics of this runtime. So we also notice that the runtime is very different for even and odd problem sizes, and for even n it was much easier to find the optimally diverse population, and this is probably because the optimal diversity is reached in like the optimal balance for each position is much more flexible in this case, because we can either n over 2 or n over 2 plus 1 bits in that position. So the big problem in the theoretical analysis in our last year paper came from individuals which are neighbors in the Pareto front and which are in distance one from each other, because they didn't allow us to stay for long enough in the good state when we have lots of 2-bit flips to get to the optimal population, because it is quite easy to flip 1 bit in one of those two neighbors and get individual which replaces another neighbor, and it leads to unpredictable changes in the population. And taking this thing into account during our analysis led to unrealistic leading constants. So we decided to see if it actually what happens in practice. So we looked at several typical runs, like with natural initialization. We noticed that actually natural initialization often starts with the second best diversity, or sometimes it even starts with the optimal diversity, which means that the tie-breaking rule actually optimizes the diversity before we reach the Pareto front quite effectively. We saw, like, we looked at this run and made snapshots of the Hamming distances of the neighboring individuals in the Pareto front at these points of time which are marked with red lines, and we see that actually at all moments of time we didn't have lots of individuals in distance 1 from each other. For example, we have only these two and this, so only 3. And here is the video of this. We also see that there is no many changes happening during this run. We also considered a different kind of initialization, which is the worst initialization, when actually all our individuals start in distance 1 from each other. And we also took 5 snapshots, and black points mark the difference from the previous snapshot, and we see that even in the end of the optimization we still have lots of points in distance 1 from each other. And let's see the video of this. So we see that first the diversity grows really fast, and then we have we reach the second best diversity, which is 2 here, and the changes still happen quite a lot. Note that this video is much slower than the previous one, but we still find the optimal diversity quite fast. Okay, and our last result is the population which is impossible to escape with only 1-bit flips and which has the second best diversity, namely it has all positions balanced, but the first position has 1 0-bit and the last position has one extra 1-bit, so we called it cold position and hot position. And this population cannot be, like here we cannot replace any individual with a 1-bit flip, because 1-bit flips only create neighbors. And for example, all 1s and all 0s between just cannot be replaced because they are unique for those levels. These individuals with 1 in the beginning and 0 in the end cannot be replaced, because if we replace it with a different one, then we either increase 0 bits in the cold position, or increase the number of 1 bits in this position, in the hot position, or we unbalance all of these positions. All of those will decrease the contribution of those positions changed, and it means that we can replace it with something better. And these individuals cannot be replaced because any 1-bit flip of their neighbors will generate a bit string which is too far away from this individual, so we unbalance many positions. We unfortunately don't have time to consider it in details, how we build this population, but just to conclusion, I must say that evolutionary diversity optimization is described with really complicated processes and which are hard to analyze. However, empirical studies can also give many new insights for the theoretical observations. We also noticed that despite the complexity of the processes, they don't take much more time to find the optimal diversity than it takes to find the Pareto front. And we also noticed that the diversity is also optimized immensely on our way to the Pareto front. So thank you so much. I will be happy to answer all your questions.